Hello, and here it is, my first ever video lecture. Still some bugs and kinks I need to work through and figure stuff out, but hopefully this will be much better than the written lectures. And I'm going to try something a little bit different here. I am using a Word document on the left and PowerPoint on the right here to try to take advantage of some of the color and graphing that I can do with the computer to hopefully demonstrate things better. And without further ado, let's begin. So we're taking our next big step into calculus, and that's going to be integrating. Before we get to that, which will be next week, let's first begin with how we derive and what this means. So the question that we want to answer is, what is the area between a function and the x-axis from 2 points? The beginning point A and the final point B. So to demonstrate this, just use PowerPoint over here and just pull up a regular old graph. And I'm going to start simple here, just with a constant function. So we'll just take it at 3. And now we want to have the area between the function and the x-axis here, and between 2 points A and B. And I'm just going to put these points somewhere. You can put them wherever we want. I'll stick them there. And we want to figure out what this area is. Now, as you can see, it's obviously a simple rectangle, and we're going to start with geometry to figure all this out. So, from geometry, we do know the area of this rectangle is length times width. And that's something that we can just easily write down then as our first formula to begin with, that we can have length times width. Now this is the very general formula for geometry. We need to get it to be a little bit more complex so that we can deal with harder functions that are not just squares. So to do that, we're going to first start to take these L and W values and try to writing them in something that's more function oriented instead of just these letters L and W. And an easy spot to begin here is to start with L. We look at L here, we can see from the rectangle that L is simply going to be B minus A. That will be the length of L, and that will always be true for a rectangle, and that's our next equation that we can get from this, as we will have L equals B minus A. And if we look at our rectangle over here as well, we can see that W, the width here, is actually just the height of the function. And so we can go ahead and write that as our next equation, that we're going to have W equal to our function. Now, this is only true for constant functions. We'll adapt this to more advanced things, but we got to start simple so the ideas come across. So given these two new expressions, we can then express A in terms of these new expressions. So now we're going to have that A equals, instead of L, we're going to have it as B minus A. And instead of W, because we know W is the function, we can just replace that in there. And this is still the same area formula as you're familiar with, length times width. It's just written differently. So this new expression for A is actually going to be our starting point on how to set up for more advanced things. And what we're going to do now is going to seem a little bit strange because we're going to be dealing with just the simple rectangle here. But I'm going to split this rectangle into 2 rectangles. And we're going to get the answer again for the area under the curve, but using 2 rectangles. I know this doesn't make too much sense and why you would do this for a rectangle, because you most likely wouldn't, but this does help us develop where we're going to go to. So the next question that we want to answer then is, what is going to be the area then between a function and the x-axis between A and B using 2 rectangles? So if we look at our rectangles over here, let me put some L's and W's on there. These rectangles are going to be split evenly. All our rectangles will be split evenly. They do have the same length. And if we look at this expression for the length now, it's a little bit different than before. So because now we have b minus a, but it's divided by 2. So our new expression here for L, now that we have 2 rectangles, so the expression for L now would be b minus a divided by 2. And this is our new expression here for L. And of course, W here is still going to be the function height. And so we can add that in there. That hasn't changed. And now we have L and W now expressed in these different letters. So now, to figure out the area of this rectangle, we're going to actually sum together 2 of these rectangles. So we can say that the total area of our full rectangle is going to be the area of one of the rectangles, say the green one, plus the area of the other rectangle. We'll just call that A2, the red one. So it's slightly more complicated than before because we're breaking it into 2 rectangles here to solve the problem. And now it's just a matter of determining what A1 and A2 are and then adding them together. So we know, using basic geometry again, what the area is for these rectangles. So we could write, say for the green rectangle, area 1, that we know that this is length times width from geometry. But we also have now our new expressions for length and width. So if we look over here, our expression now for length is b minus a over 2, and w is still our function. And this would be our expression then for the green rectangle. And likewise, for the red rectangle, which is area 2, it's actually the same thing because they're both the same rectangles. So here's our expression for the 2 rectangles that we're going to add together then to get the total area. So if we do that, you can see that these both are exactly the same. So the total area is going to be simply adding these together, which means we have 2 of them. And then we still have our b minus a over 2, and then our function height. And as you would expect, of course, these 2's cancel out, and we get the same formula that we just had previously of b minus a times the function, which is what we should expect since we should get the same answers. But the point here is that this strategy that we're going to use of splitting the area into multiple rectangles and then adding these rectangles together. That's the strategy we're going to do. And it's much easier to understand this with a horizontal line before we start to get into curvature. So I'm going to continue more with this horizontal function and split it into more rectangles and see how that works out. So let's now take our 2 rectangles and break them into 4. Now we could break them into 3 or 5, but it's actually drawing wise for me easier to keep these even, the number of rectangles. So what we're going to do now is figure out the area using 4 rectangles here. And this is what it'll look like. I'll split them all up. We now have 4 rectangles to figure out the total area here under the curve. And of course, there's still height W, but L, you can see, is shrinking. So L, the length of a rectangle now, is getting even smaller. And then it's an expression that we can write down. But first of all, the total area that we're going to have here then for our rectangle is going to be the sum of A1, A2, A3, A4, all meaning the sum of all of these areas, the red, yellow, green, and blue, add them all up. That will be the total sum of our rectangle. And we're going to do the same thing we've been doing. We're going to get different expressions for L and W and plug these in. So if we look over here at L, now it's also important to remember that these rectangles will always be evenly split. So all these rectangles all have length L, and they For the constant function, they all have the same w. The w will change when we have curvature, but the L will always be the same. The rectangles will always be the same thickness. So our expression for L here then, if we look at this, is we now have L is going to be b minus a, so the total distance, b minus a, but we're dividing it by 4 now, since we have 4 rectangles, and so our new expression is simply b minus a over 4. And that would be our expression for L. And of course, w is still our function height. That's not going to change with constant functions. And this leads us to our full expression then for A. So we know that, say, A1, and we want to figure out what the area is for A1. Well, that's something we can write down. Again, all this comes from the geometry of a rectangle. We know it's length times width. And we know that the length is b minus a over 4. And we're multiplying that by the width, which in this case is simply the function. So that would be the area 1. Say, we'll call area 1 the blue rectangle here. And this area expression is, of course, the same for all the rectangles since they're all the same. So when we take the sum of all 4 of these, then that means we're simply going to have 4 of these expressions, and we can add them all together. So our total area here now is going to be 4 of these b minus a's over 4 times the function. And again, these 4's cancel out, as you'd expect, and we get back our formula that we should have, which is simply length times width for our total value of the large rectangle. Now, it's maybe a little bit tough to see, but if we look previously at 2 rectangles, we had a 2 here and a 2 here. And for 4 rectangles, we have a 4 here and a 4 here. And this pattern actually continues for how many ever rectangles we want to squeeze into this area. And so instead of writing a 4 here, I'm just going to use n. N is going to mean the number of rectangles. And that's what it'll mean throughout the lecture and your book. N is very commonly used for the number of rectangles we're going to use. And so our general expression then is going to be this. For how many ever rectangles you want to choose, that's what n is, and that will always give you the total area between the curve and the x-axis. And this formula, now that we have an n in here, is starting to get us closer to where we're going, because n is going to be the number of rectangles, and eventually we're going to let n go to infinity. We're going to squeeze infinitely many rectangles into this region. And we can't quite do that yet because we're still in the domain of algebra. And to start dealing with infinity, we will have to get to calculus. But that will be for next week. Everything today is actually algebra. But I'll mention some calculus stuff here and there. So to proceed forward here, we're actually going to need some more advanced notation. Because eventually, we are going to have so many rectangles in here that it's just going to be too cumbersome to gather all these terms together. I mean, imagine if we squeezed in 1 billion rectangles here. That'd be 1 billion terms you have to add together. And that's just, something you're not going to want to do by hand. And so to handle these much longer expressions, we're going to use what's called the summation notation. And a summation is this Greek symbol S. It's the sigma symbol. And it helps us write out expressions that are indexed. So if we go back to our area formula from before, it's indexed. And that index is what we need for summation notation. And I want to check out the equation editor here and have you look at it for a second, because I think it's pretty useful and how it shows the summation symbol here. So here's our sum symbol. And what always goes in this big first box right here, that's our function. This is the thing that we're going to be summing here, whatever's going to go there. And at the bottom, in this box right down here, this indicates the indice that we're going to start with. So if we look at our expression, we're going from 1, 2, 3, and 4. So we're starting with 1. And that's what we would put here. We would say we're going to start with 1. And we're going to end with 4. And where we end goes on the top. So start on the bottom, end on the top. And the summation symbol does use integers. So the I will go 1, 2, 3, and 4. I will never be, say, like 1.5. In the summation notation, it's understood that I increments by 1. And this allows us then to write a compact expression for what our area would be. So if I take this formula and we look at what our area is, what we would then have to do is we would simply write this then as A sub I. And this A sub I represents then writing all this stuff out. A sub 1, and writing all this stuff out. And again, if we had a billion terms right here, well, this would take me forever to write out. But with the summation symbol, it's really simple because I could just put a billion on the top and be done with it. But this is what the summation symbol is and what it does. It's more like a machine telling you to add things as you progress. And we are going to be using this symbol so we can handle more rectangles under the function. But first, before we get into doing any of that, since the summation symbol may be new to some people, let's just do a quick few examples on how you would use this summation symbol. And I'll just make something up here. And let's just say we have some new expression. Just call it B sub I. And this equals 2 times I. And what I'm going to want to do here then, and we'll say we'll do this for 4 here, is let's say we want to sum this. So here's our expression. We have B sub I. We're going to go from I equals 1 to 4. So first we start with 1. So we have I equals 1, so we have B sub 1. Well, what does B sub 1 equal? Well, we'd go to our expression right here for B sub I. If I is 1, then we'll just plug I in, which means B must be 2. And once we've done our first term, we're done. And now the summation symbol means we're now going to add the next term. Now the next term means we increment I up by 1. So now I becomes 2. And so now we'll take 2, look at our expression for B sub I. So if I is 2, then we have 2 times 2, which will get us 4. And then the summation symbol says, okay, great, now add the next term. And so now I is 3. So if we look at B sub I here, now that I is 3, then 2 times 3 means we have 6. And the summation symbol says, cool, well, keep doing that. Add another term on there, and you keep doing it until you get to the top integer, which is 4. And that's what we're at now. We're at 4, so I equals 4. So if we plug that in, we have 2 times 4 equals 8. And now we're done. We've summed our 4 terms. And of course, we can just look at this and see we've got 20. And that would be our answer. That is the sum. Using the summation symbol, the sum is 20. And we can check out another example. How about if I defined another expression, let's say C, and let's call CI, let's call this I squared. Now we have this expression. And what we're going to do is we're going to sum this again with 4 terms. So now we're going to sum this as C. So we start with I equals 1. So I is 1. So we'll do on here. Okay, well, if I is 1, 1 squared means 1. So we're done with 1. The summation symbol means add your next term. The next term is when I equals 2. So now we'll look at 2. Well, if I equals 2, 2 squared is 4. And now we add the next term when I equals 3. So we'll go to our expression. If I equals 3, well, 3 squared is 9. And we keep going until we reach the top number, which is 4 here, which is where we're at now. So when I equals 4, we'll plug this in, and 4 squared is 16. And what do we got there? 20, 30. And that's our answer. This sum of C sub I from 1 to 4 is 30. So that's just a quick intro to the summation symbol. If you're actually going on further into calculus, you'll definitely deal more with the summation symbol. We don't deal with it too much right now. But a few more things to say to make sure you have some comfort with the summation symbol. Let's just keep going a little bit with summation notation. And let's get back to our area, because ultimately we want to use this symbol so that we can express all these rectangles that we're going to squeeze under the function. So here's our expression again for our 4 rectangles, the blue, green, yellow, and red, A1, A2, A3, and A4. And here is the summation symbol that would express that, summation. And we can, now the point of the summation symbol actually, one of the points, is to get rid of all this stuff on the right, because that's the stuff that takes so much work to do. And this is our more compact expression then that can represent many, many terms, depending on how high you want I to go. So, if I went to 1,000,000, this simple expression here would represent 1,000,000 terms. And if we go back to what the area actually is for a rectangle, we know that's length times width, but we're going to use our new letters that we're using with b and a in the function. So our expression for a sub I here is actually going to be our b minus a, and that's going to be for 4 rectangles. That would be 4. That's our length, and times our function. This is what we talked about before for our expression or area. This time I'm just putting this index on it of a sub I. Now, if you do look at this function, there is no I in it. So what does that mean? Well, that means as you increment through I, the terms don't change. If there's no I there, then nothing changes and it continually stays the same. So let me just quickly demonstrate what I mean by that. So if we take our sum, now I've defined what a sub I is. It's going to be this new expression here. So we can just stick that in. Instead of a sub I, we're going to have our b minus a, and that's all over 4, times the width. In this case, that's the function height. And so what does this equal as we increment it through? Well, remember, we start with I equals 1. So there's no I in our function, which means nothing changes. So the function that stays the same, and so we'd still have b minus a over 4 times the function. And that's what we get for I equals 1. And now the summation symbol says keep going, and so we'll add I equals 2. Now if I equals 2, well, nothing changes. And so we get exactly the same thing again. And that's for I equals 2. And now we're at I equals 3. Now at I equals 3, again, nothing changes. It's still the same expression. And so we would add that expression again. And Now I equals 4. So we'll add in I equals 4. Again, there's no I, so the expression stays the same. And here is the full statement then. So our sum on the left will equal adding these 4 terms on the right. And of course, if you add those all together, you'll get a 4, and those 4s will eventually cancel. So if we add all of these expressions together, that means we've got 4 of them. And those 4s cancel, and we're back to the expression that we originally started with, which we should. But again, the point here is this machinery that we're developing in order to get the area under the curve. It's all going to be about these rectangles. And then eventually we're going to take this to infinitely many rectangles. So let's get a little crazier here. Instead of 4 rectangles, let's break this into 8 rectangles. And let's work this all out and see what happens, how it's going to work out. So now we have our, first of all, remember our length. Our length is always going to be b minus a divided by how many rectangles we're going to have here. So now we have 8 rectangles. So we're going to say n equals 8. So our new expression here, instead of 4, we're now saying there's 8 rectangles. So our summation has to go from 1 to 8 to add all 8 of those rectangles. Our length, which is b minus a, divided by 8, since we have 8 rectangles, and that's still times the function height. So what does this equal actually number-wise, given this information we have on the graph? Well, if we look at b, if we look at the graph, I'm saying b here is at 8. So b is 8. And if we look at a on the graph, I'm marking a here as 2. So a is 2. And if we look at the function value, the function is always 3. So we can replace the function here with 3. And this is our expression here that we're actually going to be iterating. So let's do that. So here's our expression that we're going to iterate along. And let's do that for, actually 8 minus 2 is 6. So I'll combine that there. And again, there's no I here, so nothing changes. So when I equals 1, we're going to have our exact same expression, which is 6 over 8 times 3. And that's for I equals 1. And now the summation says, okay, great, you did I equals 1. Now go to I equals 2 and add that. Well, there's no I in the function, so nothing changes. And so we have I equals 2, I equals 3, I equals 4, 5, 6, 7, 8. And this would be our full expression then for our summation. So you can see, hopefully, that the summation symbol is a compact way to write out many, many terms. And especially when we start getting n to be very, very large, you're definitely not going to want to write out all these terms. Now for this first homework though, 4 terms is probably the max you're going to go. It's still a little bit of work, but nothing that's going to be 8 or 10. So if we did add all this together, of course, all of these terms are the same, and there's 8 of them. So we've just got 8 of these terms. And then you can see our final result here, since the 8s cancel, is just 18. Which is, of course, the answer I'm sure you've already are able to obtain just from simple geometry of length times width there. Now I do want to say something really quick here. about where this is all leading to. So our expression that we have is our algebra expression here. This is our general expression. So this summation here is going to be the basis for what we're going to be continuing to do. Now notice here's our b minus a, and we have an n now. And the n again represents how many rectangles you're going to break this area into. Now what's going to happen next week is that we're going to let n go to infinity. And in order to do that, we can't do that with algebra. In order to let n go to infinity, then we're going to have to use our favorite tool from test 1, the limit. And this is our full calculus expression that we will get into next week. We'll be tacking the limit onto this summation and letting n go to infinity to figure out what that is. But for now, we're just going to stick with the algebra expression. But this is where we are going. We're eventually going to tack the limit onto this. So we have our algebra expression. Here it is. And a common thing to do is b minus a over n. A common thing to do, and all math books pretty much do this, is to redefine this. Now, if you recall at the starting, this b minus a over n is simply the length of one of these rectangles. And now all the rectangles have the same length, and the length is always going to be b minus a over n. So that length there is always going to be our b minus a over n. But L is not commonly used for this expression. What is commonly used, though, is delta x. So again, another algebra expression using the delta symbol, which means change in x. And so we have delta x is b minus a over n. And we're just going to replace L now with delta x, because that's the common thing to do. And we're going to stick this into this summation. So now instead of b minus a over n, we're going to simply have this delta x. And then here is our evolving expression for the area under a curve, given n rectangles. So now that we have an expression, a starting point, we need to advance this now to be able to handle curvature. Since so far, this result only works for horizontal functions. So in order to get some curvature in there, let's get rid of our graph over here and start blank again. And our new question here, or our statement that we're going to do, is we're going to now use our area formula with functions that have curvature. So our area formula, again, is this expression right here. That's our area formula we're going to use. And also, delta x is our b minus n over a. These are our two expressions that we are at now. And again, area, try not to lose too much focus here. Remember, this is still length times width. Delta x is the length, and the function is the width. So it's still length times width. We are just writing it in a more advanced way so we can handle functions with curvature. Now, I think it's really important to understand here what is given to you for these problems that you're going to be doing. So when you do these problems, what is given to you is always going to be the function A, which is your starting point, B, which is your ending point, and N, the number of rectangles. So try to keep that in mind. This is the information that you are given. You won't have to figure this stuff out. You're always going to be given these 4 things, and then you need to know how to use these 4 things then to get the area under the curve. So let's start with an example. And I'm just going to start with the simplest function that has curvature, always our good old friendly parabola. And so I'm going to define a new function here, minus x squared plus 9. So if we look at our graph over here, that's what it looks like. Our inverted parabola. And of course, it has its y-intercept at 9 there. And we're going to start squeezing some rectangles in here. But all I've given is the function so far, minus x squared plus 9. I also have to give a and b, because you need to know where to start and you need to know where to end. So I'll just make some numbers up to keep it kind of simple. I'll just say a is 0 and b is 2. So we're going to start at 0 and we'll go to 2. And let's do this with 2 rectangles. So we're going to say n equals 2. And again, I want to make sure it's understood these 4 pieces of information have to be given to you. And then we will use this information to figure out how to get our answers. So if we look at the graph on the right side here, I'm going to stick these markers in here. So here's where a equals 0 and b equals 2. And then the region that we're interested in is this green region. This is the area we want to figure out under the curve between the x-axis between 0 and 2. We want to know what this green area is. And for today, we're only going to approximate this area. Algebra can only approximate this area. Calculus will eventually allow us to get the exact area. So keep in mind that everything we're going to be doing now, these are all approximations. And then next week, we will tune this up to get exact answers. Now, there is an ambiguity that can happen when we start to try to fit rectangles in here. So here's our 2 rectangles. I'm just going to split that up. So there's our 2 rectangles. Now, of course, rectangles should have a flat top, and these have curved tops. And this is where it can be ambiguous on how you top this rectangle. And there's 2 ways you can do it. So consider a straight line, because that's what we're doing here. We're drawing straight lines. So if we have a straight line, and I get to the top of the straight line, I could go right to form a rectangle. So I could go up and right. And now the other thing we could do is go up and left. And these are the 2 possibilities you can do for creating rectangles. And unfortunately, there is not a standard naming convention for this. If you go up and to the right, that's called a right rectangle that you're forming. Some people also like to call that the left endpoint, since your rectangle starts from the left. And if you go up and to the left, this is then called a left rectangle, because it's going to the left. However, it can also be called the right endpoint because you're starting on the right side of the triangle. So I know that can be confusing, and books do vary on what they say. So we have these 2 ways that we can introduce rectangles into our picture. And so let me show what that looks like then. So on this left graph, I have these right rectangles. So I drew my line straight up and then to the right. and then I drew my line straight up and to the right, and I formed these two rectangles. So that's our right rectangles. Now if we go to this other graph, notice that at 0, if I start at 0 and draw a line straight up, I can't go to the left because that goes outside our region of interest. Remember, we're interested in 0 to 2. So I can't draw a rectangle to the left. So for left rectangles, we actually can't start at the starting point, and we have to move to the next line over, this middle line. So this middle line, we draw the middle line straight up to the function and off to the left. And that creates then our left rectangle. And then we go off to the next line here, which is at 2. And so we draw our line straight up and to the left. And so here is our left rectangles. And here is our right rectangles. And you can tell there is a difference between them. And they do algebraically give different answers. However, once we introduce calculus, these will both give the exact same answers. But for now, you should expect these to be different. So this right rectangle, if you notice, I'm filling in this pink here. So for right rectangles, this pink region represents an overestimate. In other words, these rectangles are going to give us too large of a value because it's going outside the function. And when this happens, another name that can happen here, unfortunately, is upper sum. So there are some people that also like to call this the upper sum because it's an overestimate of the area. And if we go to our left rectangles, notice the left rectangles are always below the curve. And so the pink region over here represents an underestimate. And so it's common for some people to call this the lower sum, since this will give us the lower estimate, and this one over here will give us the highest estimate. And let's just focus on these one at a time. And so let's focus solely on just right rectangles. So I'm just going to take the right rectangle graph, here it is right here, and I'm going to zoom in on it just so you can see things a little bit clearer. So I zoomed it in over here, just cropped it up a little bit. So I'm going to take this zoomed in picture and start with that. And I put the function here just to remind you of our function here. And it's important to remember, right rectangles always start at A. In other words, our right rectangles always start at our beginning point. And what we're going to need to do here is start labeling where these rectangles are starting. So you can see I'm going to start labeling these x1 and x2. So our first line here that forms our right rectangle, I'm going to call it, starts at x1. And our second line that starts the second rectangle is at x2. And a challenge for us here is going to be then to figure out what these x1 and x2s should be. And one last thing about right rectangles when you draw these, there's no right rectangle at B. So B is this last black line here. And notice if we draw this line straight up to the function and then draw a rectangle to the right, that this goes outside our region of interest. We're not interested in anything beyond B, so there's no right rectangle at the very last point. Again, I'm flashing in here the thickness of these rectangles. Remember, they're always going to be the same. And we're going to call these thickness delta x. And this delta x we can figure out from the information given and that we know delta x is b minus a over n. So if we look at that, delta x right here, we know that b is 2. We know that a is 0. And we're going to use 2 rectangles, that's n. And so we get a delta x of 1. And that's what we had to figure out from our information given. We had to figure out what delta x is. So for right rectangles, let's just focus on right rectangles, this one here. What we need to figure out is an expression for these x1 and x2 values. And again, if we have 100 rectangles, then we're going to have 100 of these x values. And so we need some expression that's going to represent all these values. So if we look at x1, our first rectangle always starts at a. And so that tells us then what x1 should be. That x1, our very first starting point, has to be a. Because that's where our first rectangle is going to start. And so for right rectangles, x1 is always a. That's always our starting point. So the question is then, okay, well, if we have x1, then what would x2 be, our next increment over? So we want to know, what is x2? So if we go back and look at our graph here, well, x2 is delta x away from x1. So we can say that x2 is going to be x sub 1, our starting point, plus delta x. And this gives us an expression for x2. However, we already know what x1 is. We just determined that right here. We determined x1 is a. And so let's just replace x1 with a. And that is our expression for x2. The value at x2 must be a plus delta x. And delta x, we already figured out, is 1. Now there's only 2 rectangles here, but I do want to show you what the general formula is for x. So just for a moment, assume there are more than 2 rectangles. And let's say we had to figure out the third value here. Let's say there was a third rectangle and we had to figure out what that is. So we want to know what our x sub 3 is. We want to know what this equals. So x sub 3, if we would continue on, would be at this last black line right here on the right. Now notice this black line here is a delta x plus delta x plus x1 away. So we can say that x3 is x1, our starting point. And then we're going to add to that a delta x and a delta x. So x3 would be x1 plus 2, the delta x away. And again, we know x1 is a. So if there was a third rectangle, we would have this expression then for x sub 3. The third rectangle would be located then at this position. And let's just do one more. Assume there would be a fourth rectangle. Well, where would that be located at? Well, we would have x sub 4. And so x sub 4 would be at this gray line here, the end of my graph I have right here. And so that would be x1 plus 1 delta x plus 2 delta x plus 3 delta x. So x4 would have to be at the position then of x sub 1, our starting point, plus 3 of these delta x's. And again, we know x sub 1 is a. So let's just replace that. And if you look at these expressions, maybe you're seeing a pattern here. And that pattern we can then understand and determine the general formula for all the x's. So notice, x sub 4 has a 3 here. X sub 3 has a 2. X sub 2 has a 1. And x sub 1 has a 0. And so from just recognizing this pattern, we can determine what the general formula for x sub I is. In other words, any point you want. They all start with a. And again, notice 4 goes to 3. 3 goes to 2. 2 goes to 1. 1 goes to 0. And so this gives us an expression then that is I minus 1. So when I is 4, we get 3. When I is 3, we get 2, and so forth. And this is what's being multiplied by delta x. And this right here is our pretty big deal because it's our general expression for right triangles. Right rectangles. This will give us every x sub I position. So for instance, if you want to know what the 10th position is, x sub 10. Well, if I is 10, 10 minus 1 means 9 delta x. And that's our position. But let's go back to the graph we're doing on the right here with just 2 rectangles. I wanted to show you 4 rectangles so I could get to the general expression that we'll be using going forward. But let's go back to just using 2 rectangles and finish off the problem we're working here on the right. So if we look at this area over here, we're going to add these 2 rectangles together, just like we did with the horizontal line. So we're going to have our area then is going to be the first rectangle. Now the first rectangle has a height that's the output of the function at x1. So to get the height of the first rectangle, we are simply plugging x1 into the function. Plugging x1 into the function gives us the height of the rectangle. And then we simply multiply by delta x to get the area of that rectangle, length times width. And then we're going to add to that the second rectangle. Now the second rectangle has a shorter height, but its height is still located at an input of the function. So to get the height of the second rectangle, we're going to input x2 into our function to get the height of the second rectangle. So we'll just do that. And then to get the full area again, we're going to multiply that by delta x. And that's our expression, our approximation for the area under this curve. This expression, I do just want to quickly write back into summation notation, just so you can see what that looks like. So if I took this expression and wrote it in summation notation, we'd have to look at our index here. So that's a 1 and a 2. Our index is what we then write as I. So this would give us f of x sub I being our index, times our delta x. And remember, the bottom of the summation indicates where I starts. Well, if we look over here, we're starting at I equals 1. And the top of the summation tells you where to stop. And we're going to stop when we get to 2. And that would be how we write the expression then with our summation notation. So this is where we're at. We have our expression for the area. We have our delta x. I'm just going to write it all down here so we can combine it all. We have our expression for the area. We have our delta x. And we also have the xi positions. So these three things right here are key to getting our approximation. We need all three of these things. So let's check it out for this problem. Now, what do we know here? Again, remember the information, there's information that has to be given to us in order to do these problems. So what we know is we know that A equals 0, B equals 2, and so that tells us that delta x is 1, which we figured out a few minutes ago. So we know from the information given and using our equations here that we have a delta x of 1. That is the thickness of our rectangle. And what else do we know? Well, we know x sub 1 starts at A. And we know A is 0 for this problem. So that means then x sub 1 is 0. And now that we have x sub 1 and delta x, we can then figure out what x sub 2 is. So we can use our formula right here. When I is 2, 2 minus 1 is 1. So we'd have A plus delta x, and A is 0. So we know for x sub 2 that we know this equals A, which is 0, plus, I'm looking at this formula right here. You know, A is 0, our index is 2, so I is 2, so 2 minus 1 is 1, times delta x, but we already figured out what delta x is. It's right here. It's 1. So then that tells us what x of 2 is. It's 0 plus 1, which is 1. So let's take our expression here that we have for our area. Just going to paste it down here. We can stick it by our information we know. And I'm just going to get rid of the summation symbol here since we are going to figure these two terms out by hand. So what does this equal? What does this total area equal here? Well, the first thing it says here is to take x1 and plug it into the function. And x1 we figured out is 0. So we're going to take this 0 and plug it into the function. Minus x squared plus 9. And plugging 0 into that gets us 9. Now it says that we should multiply this by delta x. And we figured out delta x over here. We figured out that's 1. And so 9 times 1 gets us our 9. And then we have our plus sign. Moving on to the next term. The next term says take x2 and plug it into the function. So what's x2? Well, we figured out what x2 is. It's 1. And so we'll plug it into the function. And 1 squared is 1. So 9 minus 1 is 8. To give us our final answer then of 17. And that is our answer. Our approximation for the area under the curve with two rectangles is 17 units. units, meters squared or feet squared, inches squared, whatever units, but that would be 17. So now that we've done 2 rectangles, let's beef it up a little bit. How about 4? Now I am zooming in on the graph here so that you can see it better, because I'm trying to squeeze more and more rectangles in here, which makes the picture tinier and tinier. So I'm going to zoom in on that. And you can see I now have 4 rectangles squeezed into this area between 0 and 2. And all of these rectangles have the same thickness of delta x. That's always going to be true for our rectangles. And we can figure out what that delta x is, because remember, it's over here. It's our b minus a over n, where b is 2, a is 0, and n is 4. And so here's our delta x of 2 minus 0 for b minus a, 4 for our 4 rectangles, which means that delta x is now 2 over 4, which reduces to a half. So with 2 rectangles, we had delta x of 1. With 4 rectangles, our delta x is now a half. So now the question we're going to try to answer is, what is this area if we use 4 rectangles? So let me write out, I think it's always important to understand what is going to be given. Now again, what is given is the function. I'm giving that to you, the minus x squared plus 9. I also have to give you the starting point, which I'm saying is a equals 0. I have to give you the end point, which I'm telling you is b equals 2. And then I have to tell you how many rectangles to break this into. And so I'm saying that's n equals 4. This information will always be given to you for these problems to do. So you don't have to think about this. You simply have to identify this information in the problem. The part you have to think about here is the stuff you got to figure out. And how we're going to figure this stuff out is the equations that we've been using. So we have our, first of all, we already figured out what delta x is. And so that's a good piece. We're going to need that. So that's good to write down. We already figured out that delta x is a half. And once we have delta x, we really want to start labeling where these rectangles start. So I'm going to start right here with x sub 1. Now remember, for right rectangles, x sub 1 will always be a. So we have then, for our first x value, x1 equals a, and a is 0. And so that's our first position for x1. It's 0. Now recall, to get the other positions, I'm just going to copy this expression down here. To get the other positions, we're going to use this expression. So let's get x sub 2. And with x sub 2, that means our index, our I value, is 2. So let's look at our expression here. It says this must equal a. We know a is 0 plus I minus 1. Well, I is 2, so 2 minus 1 is 1. And then delta x. Now, of course, 0 we can just erase, so I'll just get rid of that. And so we can see x2 is delta x. But we already know what delta x is. We figured that out. We know delta x is a half. And so we have x sub 2. So that's this second position right here, where the second rectangle is going to start. So what about this third position? Well, we'll keep using our formula. This is our formula that gets us all the x positions for right rectangles. So let's check that out. Our x sub 3 position, now I is 3. So we'll look at our formula here again. It says it must equal a for this problem, which is 0. And then we're going to add to that I minus 1. Now in this case, I is now 3. So 3 minus 1 gets us a 2 times delta x. Now delta x, we know what that is. It's a half. So we have 0, which we can just erase out of there, and 2 times a half, which is 1. And that is our x3 position. x3 is at 1. So now we want to go to the fourth and final rectangle and find out where that one starts at. And again, we're going to use our formula. That's why this one is a pretty big deal here, because we're going to use this always for our right rectangles. And by the way, I will give a summary at the end that condenses all this information if you just want to have something compact to look at. But for now, let's just keep working this through. And so our x sub 4. Now I equals 4, so a, again, a is 0, but I'll just write that in there so you can see that. We have 0 plus I minus 1, so now I is 4. So 4 minus 1 gets us a 3. 3 times delta x. We're doing 3 times delta x, but we know what delta x is. It's a half. And we can erase the 0. That doesn't contribute. And so we have 3 times a half, which is 3 halves. And that is where our fourth position is, where the fourth rectangle starts. Now that we have these positions, we use these positions to figure out the height of each of these individual rectangles. So x1 gives the height of the first, x2 the height of the second, third the third, the fourth and the fourth. And so that's what we need to do next, is now that we have our x1 values, we're going to use these to figure out what the height is. Let's do that. Let's first figure out what the function is when we put in our x sub 1 value. So we want to know, what is the function when we plug in our x sub 1 value? So our function again is minus x squared plus 9. x1 is 0. So we're going to plug 0 into our function, which means that simply equals 9. And this 9 is the height of this first rectangle. Let's go on then to the height of the second rectangle. So the height of the second rectangle occurs when we plug in x sub 2. We're going to plug in x sub 2. That'll give us the height of our function. And what is x sub 2? Well, that's something we already figured out. Over here, we figured out that x sub 2 is a half. So we're going to plug a half into our function. So we have a half squared. So a half squared being a fourth. So we have 9 minus a fourth. So what we've got here is 9 minus a fourth. And we have to do a common denominator here of 4. So this is all ultimately going to be 9 is going to be 36. So our 36 minus 1 will give us then, adding these two together, a 35 over 4. And that is the height of the second rectangle. And we want to do this for all the rectangles. So that means we have to go to x sub 3 now. So we're going to plug x sub 3 into our function. And what is x sub 3? Well, we figured that out. X sub 3 is 1. So we're going to take 1 and plug it into our function. So 1 squared is 1. 9 minus 1 is 8. 8 is the height of the third rectangle. And then our last rectangle has a height when we plug in x sub 4. Let's do that. We plug in x sub 4 into our function. Well, we already figured out what x sub 4 is. It's 3/2. So we're going to take that, plug it into our function. 3/2 squared is 9/4. So we're going to have 9 minus 9/4. Again, we're going to have to do a common denominator here of 4. So 4 times 9 gets us a 36. And then 36 minus this 9 will get us a 27 over 4. And that is the height of our fourth rectangle. And so here we go. These are ultimately the values we're trying to get, because we already figured out what delta x is. Delta x is easy to get. That's the thickness of these rectangles. The majority of the work here is actually getting the height of the rectangles. And that's what I have in blue here. These are our heights of the rectangle. We now have all of our numbers to crunch this out. So what are we going to do here? We're going to take all this stuff that we just got, and we're going to plug all of this in to our general equation for area. And here it is. All this information we did here, we're going to plug into our summation to get our answer. So let's do that. So here is our summation. We first start with index 1. So I equals 1. So we're going to have f of x sub 1. Whoop. It's not like in there. X sub 1 times delta x. That's our first term, plugging in 1. And now the summation sign says, great, now add the next term when I equals 2. Well, when I equals 2, we have x sub 2 into the function. And we're going to do this for all of them. So now we did I1, we did I2, and now we're going to do I3. And then finally, I4. So maybe getting a little ugly looking, but this is our expression here that will get us our answer. Now notice, and this is always true, Notice if you look at this expression here, actually let me just copy this really fast so I don't make it too long looking. If we take this expression here, notice that each term has a delta x. This will always be true. And we can factor that out. We can factor out all those delta x's. It's our GCF, our greatest common factor. And it's actually pretty common to write the delta x last, which will be a little bit more meaningful next week when we see where we're going. But it's pretty common to write the delta x last here. Now, all I did here was factor it out. Delta x is the greatest common factor, so that's just factoring. And this is our area expression. Now, if you look above, we've already figured out what all this information is. It's just a matter now of plugging it in. So if we look at this expression and the numbers we've already figured out right here, we can see then that f of x sub 1, which is right here, is 9. F of x sub 2 is 35 over 4. F of x sub 3 is 8. And then f of x sub 4 is 27 over 4. And all of this will be multiplied by delta x. Delta x, which we already figured out, is a half. So if you like some numbers, we'll just finish this off real fast to get our final answer here. And we would have to do a common denominator for all this. So a common denominator for 9 here will get us a 4 and a 36. And 8 with a common denominator of 4 would get us a 32 over 4. So now we can add all those together fairly simply. We got 71, 103, and 130. So we've got 130 over 4, adding all those fractions together, times a half, which was our delta x. So our final answer would then be 130 over 8. Now, yeah, you can simplify that. Not going to, I guess that's actually not too bad, only division by 2 there. So it would have a 65 over 4. And that's our final answer. 65 over 4 is our approximation for the area under the curve. And that's what we get for right rectangles. Now we'll come back to right rectangles again, but let's go check out what happens when we do left rectangles. So we're going to do all of this that we're doing. But now our question is going to be, what is the area if we use 2 left rectangles? So let me adjust the graph over here to our left rectangles. So here is our left rectangles from previously. And I am going to zoom in on this so that we can see a little bit better detail here. Here's our 2 left rectangles. the pink area representing the underestimate here. The area the rectangles aren't filling in. And left rectangles always start at the second position here. So unlike right rectangles, where we started at A and drew to the right, notice that's not done here. At 0, this black line just goes straight up to the top. We can't draw left because that goes outside our region of interest. So we simply can't draw a left rectangle there. So left rectangles always start at A, our starting position, plus a delta x away. So here is our first position for left rectangles. It's a delta x away from our starting point. And this is always true for our left rectangles. Now let's not forget our main expressions here, and these expressions are the bulk of what you'll be doing in the homework. We have our expression for the area. Here, n equals 2, because we're using 2 rectangles. And delta x is always b minus a over n. Again, n being our number of rectangles here. In this case, 2. Now, what we did previously with right rectangles is we used this expression. But this changes for left rectangles. So for left and right rectangles, these two expressions are always the same for left and right. What changes for left and right is this expression here. So we need to change this expression so that it works with left rectangles. And so we just need to think about this for a moment. Our first left rectangle always starts delta x away. And so that's enough information to tell us what x sub 1 must be. X sub 1 must be our starting position, which is A, plus delta x away. That's where this first starting position is right here. It's delta x away from our start. Now for this particular problem, A is 0. And so we can just get rid of that. And I guess I didn't write that around here yet, but we also know what delta x is. And let me actually do that really fast, since I forgot to stick that in here, is we can figure out what delta x is from the information given, because it's always going to be b minus a over n. So we have delta x is going to be equal to b minus a over n. So we know b, we look down here, b is 2, minus our starting position, which is 0, and we have 2 rectangles, and so our delta x for this case is 1. So now that we have delta x, we know what x sub 1 must be. It must be 1, because that's what delta x is. So now that we have x sub 1, what is x sub 2 right here? Well, x sub 2 is delta x away from x sub 1. And let's just write that down. We know that x sub 2 is x sub 1 plus this is delta x. But we know what x1 is. We just figured it out. It's 1. Let's replace that. We also know what delta x is. We just figured that out. It's 1. So x sub 2 must be at 2. And these are our positions where the left rectangles are. Now, I want to work towards the general expression for left rectangles. So let's assume that we have more rectangles here. Now let me just write the general expressions. So we know that x sub 1, remember x sub 1, the left rectangle always starts at a plus delta x. That's always the first position where our left rectangles start. And now we know the second position, x sub 2, is always going to be x sub 1 plus delta x. Again, you can see that right here. Here's x sub 2. It's x sub 2 is simply x1 plus delta x. And that'll give us our x sub 2. And we know what x1 is. We just figured it out. x1 is always, for left rectangles, a plus delta x. Let's substitute that in. x1 is a plus delta x. So you can see we actually have 2 delta x's here, so we'll just add them together. And that is our expression for x sub 2. Now let's pretend for a moment that there's more rectangles and that there's a third one. Now a third one would start right here at the end of my graph right here. And the third one would be x sub 2 plus delta x. Again, hopefully you can see that right here. We'd have x sub 2, and then we go a delta x to the right, and that gets us to x sub 3. And we know what x sub 2 is. We just figured it out. X sub 2 is a plus 2 delta x. And hopefully you can notice here then, we have 2 delta x plus delta x to give us a total of 3 delta x. And I don't know if you can see the pattern that's emerging here, but let me just write down what the fourth one would be. The fourth one would be a plus 4 delta x. So notice the pattern that's emerged here. When I equals 4, we're multiplying delta x by 4. When I is 3, it's 3 delta x. I is 2, we have 2 delta x. And when I is 1, we have 1 delta x. And from this pattern, we can then deduce what the general expression is for any x position for left rectangles. So it must be a plus I delta x. And this is our big deal for left rectangles. This expression here is how we get the x positions where the rectangles are for left rectangles. So let's go back to the problem we're working here. We actually have two rectangles. And again, I think it's important to remember what you're given so that you know what you're supposed to be figuring out. So again, we're given the same thing as before because I haven't changed the problem at all. I've just gone from right rectangles to left. So we still have a starting position of a equals 0. We still have an ending position of b equals 2. And we're still using n equals 2 rectangles. And that's given to us. And then what we have to do with the given information is figure out the rest of the stuff. And usually the easiest thing to start with is delta x. So we know that delta x is b minus a over n. This is always the expression for delta x. So let's look at the information we have. So we are told here that b is 2 minus a, which is 0, over n equals 2, which then tells us then that delta x must be 1. And now that we have our delta x, we can use our general expression here to then figure out what all the x sub i's must be that we're interested in. Now we already did this before. For our 2, we got x1 is 1 and x sub 2 is 2. And now once we have the position of where the rectangles are, we use these numbers then to figure out the height of the rectangle. So x1 right here, this middle black line, x1 is the height of the first rectangle. And then x sub 2 is the height of the second. And that's what we want. We want those heights. And to get those heights, we plug the x value in to the function. So x sub 1. If we take x sub 1, which is 1, and plug it into the function, minus x squared plus 9, then we find out that f of x sub 1 must be 8. 8 is the height of the first rectangle. Let's go on to the second. So the second's going to be at 2. At position 2. What is x sub 2? Well, we figured it out. It's 2. So we're going to take that, plug it into our function. So 2 squared is 4. There's a minus sign there, so 9 minus 4 gets us a 5. 5 is the height of this second rectangle. So now that we have our information, so let me just summarize this again. We're given a, b, and n, and of course the function. We're given these things. Then you or me or whoever's working the problem, we then have to figure out delta x. Once we have delta x, we can figure out the positions of the rectangle, the x sub 1s, x sub 2s, and so forth. Once we have the positions, we can then plug those positions into the function to get the height of the rectangle. And now that we have the height and their thickness, we can get their area. So we're going to take all this information that we've been given and figured out and plug all of this in to our formula for the area for 2 rectangles. So here's our summation notation. I goes from 1 to 2 because we have 2 rectangles. And then writing this out, we have f of x sub 1, f of x sub 2. And remember again from previous that the delta x is always a greatest common factor here that we can factor out. And so we're just going to plug our numbers into this then, because we've figured them all out. We know what f of x sub 1 is. It's 8. We know what f of x sub 2 is. It's 5. And we're going to multiply all of this by delta x, which we figured out is 1. And so our final answer here is 13. Now recall, so we have 13. 13 is our underestimate for the area. 13. Recall for the right rectangles that we ended up getting, for 2 rectangles I should say, we ended up getting 17. So 4 units higher because the right rectangles gave us the overestimate. Now I do want to be clear here that right rectangles don't guarantee an overestimate. It all depends on how what your concavity is of the function. So just because you're doing right rectangles, don't connect that with always being an overestimate, because it's not always true. The only way you can tell if something is an over or underestimate for complicated functions is to actually crunch out the entire number and see which one is larger and smaller. And we'll do that. But I just wanted to stress, don't connect upper sum with right rectangles. And likewise, don't connect lower sums with left. That just happens to be the case for the problem I'm working here, that it turns out that way. So we've done 2 left rectangles. So let's bump it up. Let's bump it up to 4. Now I'm going to zoom in here. I'm zooming in because it's getting pretty complicated, the picture, so you can see everything. So the same function, minus x squared plus 9 from 0 to 2. Here's our 4 rectangles. You can see the pink area is getting smaller. The more rectangles we add, the better our estimate is getting. So let's figure out what this is. So our next question here is going to be then, what is the area for 4 left rectangles? So let's look at our equations. What are the equations that you're going to be dealing with? And here they are. These are our 3 equations for left rectangles. Now remember, these first 2 are always the same whether it's left or right. The only thing that changes for left and right is your x sub I values. So here are the x sub I values for left rectangles. So here's our 3 equations that we're going to get our information from. And let's go back again. Let me write down what is given here. So remember again, what is given is our starting point, our ending point, and n, the number of rectangles. Given this information and our 3 equations, we can figure then everything else out. So delta x is the best place to start. So we need to figure out delta x. And that's easy enough. Just b minus a over n. And if we look at our information, we can see b is 2, a is 0, and n in this case is 4. And so now we have a delta x that's a half. 2 over 4. Once we have delta x, we can then figure out where the positions are of these rectangles. So recall, x sub 1 always starts at a plus delta x. So x sub 1 always starts for left rectangles, always starts at a plus delta x. But we know what this is. We know a is 0 because that's given to us. So it's a 0, so we can just get rid of that. And we just figured out what delta x is. It's a half. So x1, our first position, is a half. Let's go on to the second position over here. This is where the second rectangle starts. Now remember, these are left rectangles, so we start at x2, go up to the function, and draw to the left to get us our left rectangle. And let's figure out what that x2 value is. So we have x sub 2. Now we know this equals, again, looking at our general form, our x sub i's, it's going to be a plus I delta x. We know a is 0 plus I. Now in this case, I is 2 times delta x. Now, of course, 0 is meaningless to add there, so we can just get rid of that. And we also know what delta x is because we figured that out. We know delta x is 1/2. So 2 times 1/2 then tells us x2 is 1. This second rectangle starts at 1. So what about the third? X sub 3. We're going to do the same thing. We're going to use our formula for the x positions on left rectangles. We're going to have x sub 3 then is going to equal a, which is 0, plus I delta x. Now in this case, I is 3 times delta x. Adding 0, meaningless, so we'll just get rid of that. And delta x, we know. It's a half. So 3 times a half is 3/2. And that is the position of the third rectangle. The third rectangle at x3 is 3/2. So the last thing we need is x sub 4. Again, we'll use our expression for the x positions. And so, x sub 4 would have to be at a plus ix. Now, in this case, I is now 4 times delta x. Delta x, which we know is a half. So 0 plus 2 gets us 2. And here we have then our 4 positions for the rectangles. The first rectangle is at a half, the second at is 1, 3/2, and then the final rectangle right here all the way to the right is at x4. X sub 4 is 2. Now that we have the positions, we need the height. Because overall, that's what we're trying to do here. We're trying to get the height of these rectangles. Because we already know the width, it's delta x. So our goal here is to get the height. So now that we have the position values, we can just plug those into the function then to start getting the height of these rectangles. So let's plug x sub 1 into that position, into the function. Now x sub 1 is a half. We're going to plug that into the function. So a half squared is a fourth. So we're going to have 9 minus a fourth. Using a common denominator there, that'll be 36 over 4. To then finally get us a 36 minus 1 to get us a 35 over 4. This is the height of the first rectangle. So let's figure out the height of the second. Now the height of the second occurs at x sub 2. Well, what is x sub 2? Well, we figured that out. It's 1. So we'll plug that into the function. 1 squared is 1. 9 minus 1 is 8. 8 is the height of the second rectangle. And we keep going. So now we'll check out what x sub 3 is. So x sub 3 right here, 3 halves. We figured that out. We're going to plug that into the function. So 3 halves squared is 9 fourths. So we're going to have 9 minus 9 fourths. We'll get a common denominator there. So that's going to be 36 over 4. And then 36 minus 9 is 27. So our final fraction here then would be 27 fourths. 27 fourths is the height of the third rectangle. So finally, to get the height of the fourth rectangle, we plug in x sub 4. So x sub 4 is 2. We'll plug that into the function. 2 squared is 4. 9 minus 4 gets us a 5. And here are our 4 heights for our rectangles. So now what are we going to do? Well, now that we have all our information, all our information being we need the heights of these rectangles. Now that we have all that, we're going to plug all this in to our general formula for the area. So we're doing 4 rectangles, so our summation goes to 4 now. Again, remember that delta x is the greatest common factor, so we can factor it out of everything here. And so what are we doing? Well, we're going to add all these function values together then. So we're going to all of these, just going to add them all together. And once we add them all together, we multiply by delta x. So let's check that out. We're going to add all of these together. So for x, so x sub 1, we got 35 fourths. And then for x sub 2, we got 8. And then for x sub 3, we got 27 fourths. And then for x sub 4, we got 5. And all of this is multiplied by delta x. Delta x, which we figured out, is a half. So there's the remaining arithmetic we got to finish up here to get our final number answer. So we'll need to get a common denominator of 4. I'm just going to kind of do that right here. So 8 times 4, get us a 32 over 4 for that common denominator. And then 5 times 4 get us a 20. That's 20 over 4 for that common denominator. Now we can add all this together pretty simply. So we have 67 94, 114 all over 4 times our delta x, which is the 1/2. To get us then our final answer of 114 over 8. And this can be reduced. They both have a division by 2 there. So that would be 57 over 4 for our final answer. So our estimate for the area under the curve is 57/4. So these sums that we're doing are commonly called left sums and right sums. And there are other techniques for doing these sums. Mostly these are used in computer programming to figure out areas under the curve through iterations. And the book does talk about one of these other techniques that I'll mention, but I just want to mention the other two. So we talked about left and right sums. The next thing the book does talk about is the midpoint sum, which we'll talk about in a moment. And the ones we won't talk about, which are actually better because they're more accurate, is the trapezoid, but the best is the Simpson sum, which will give the best estimate for the curve. So maybe you'll see that in the future if you get into some programming and have to do some iterations and figure out what some areas are. But for now, we're not going to say anything more about trapezoid or Simpson. And our last one here to focus on is the midpoint. And the midpoint is pretty straightforward. It's only got one difference from what we've been doing. So the only difference with the midpoint rule is our x sub i's. So in other words, these two equations that we have right here, these still remain the same. What changes for midpoint is the x sub I. And that's the pattern here. For the left, right, and midpoint, these two equations in blue here are always the same. What changes is the x sub i's. Each of these techniques has their own x sub I. And so that's what changes with the midpoint rule. Now, x sub I is going to be the values in the middle of the rectangle. So I'm going to try to draw that over here on the graph. So here's our left rectangle. Now the midpoint is going to split these rectangles in half. It's in the middle. So these yellow lines are going to be our new positions for midpoint. Now, what's something that is nice about the midpoint rule is that there's only one way to draw a rectangle. And that's like this over here. So I'm comparing these two pictures of what our left rectangles look like and what midpoint rectangles look like. And if you notice the midpoint, notice the pink is getting really small here because the midpoint is more accurate. So the only thing that changes here is these yellow lines. We need to figure out where these positions are. So just to save some time and having to write out this, I'll just paste it in here. So I have, so instead of a plus delta x, this is the expression that we used for left rectangles. We now have our first position, our yellow line, is going to be our starting position, which is A. And now to get halfway, instead of doing a full delta x, we're only going to do a half delta x. So our first position, this first yellow line for midpoint, is going to be A plus a half of delta x. And that'll put then the yellow line right in the middle of that rectangle. And now to get the next yellow line over, we're just going to simply add a delta x. And let me go to a better picture over here. So here's our x1 position, this first yellow line, which is at a plus a half of delta x. And now this next yellow line at x2 these are always a delta x away, just like they were previously. So the yellow lines, x1, x2, x3, and x4, and all of these are separated by a distance of delta x, just like before. So if you want to think about that expression and come up with yourself, you can do that, but I have it stated right here that the general expression then for all these xi's is going to be our starting position right here, which is a plus 1/2 delta x. That's our first yellow line. And then we add a delta x to that. Now this expression ends up turning out to be I minus 1 to get that. And we can do a little simplifying to get our final expression here for the x sub i's for the midpoint rule. So now we have this I minus a half sitting in a parentheses here. So I want to do another set of problems to show all these examples. But I do want to give a summary here to condense this information so you have something to look at. So here's our summary. When you do these problems, the problem will always give you the function, the start point, the end point, and the number of rectangles. You don't need to think about that. You just need to identify it from the problem. Now, what you do need to think about are our two general expressions. So for the area, we have our general expression here. Notice there's an n, the n indicating how many rectangles you're going to use, and delta x, which is always our b minus a over n. So we have 4 pieces of information that will be given, 2 equations that we'll always be using. Now remember, what changes for left, right, and midpoint are the x sub I values. And so here is that summary. For right rectangles, we always have this expression. For left, this expression, and then for midpoints, here's our x sub I expression. These equations represent everything that will be used in this homework. And that's our summary here. And I also want to give, in case you really like to have things ordered, another thing I kind of like of doing this presentation way is I can give you a nice ordering of things, is I want to give you a strategy. In case you're really stuck, you're really having some confusion here, here's a strategy that'll get you through. The first thing you want to do is determine delta x. b minus a over n. It's the easiest thing to do. Once you have your delta x's, the next thing you want to do is determine whether you're going to do right, left, or midpoint. Because you have to determine which x sub I expression you're going to use. So once you get delta x, you have to determine if you're going to do right, left, or midpoint. So once you determine that, once you have your formula for x sub I think a good thing to do is to list all of those out. Determine all those x sub i's and list them out, like I've been doing here. I think it's a good thing to do. Once you have all your x sub i's, remember those are the positions where the rectangles are. Once you know where they are, you can figure out their height. And that means taking all these x's and plugging them into the function. And again, I think a good thing to do here is just to list them all out. And now once you have these functions, which are the height of the rectangles, we're then going to go on and take all that information and plug it into our general formula for the area. So again, remember, delta x, you figured out. All these heights, you just figured out right here that you listed out. You stick all that stuff in there. And maybe, if you like writing all that stuff out because it helps you, then maybe you want to do that. Maybe you want to write out the summation in terms of summing all the functions together and then multiplying by delta x. So in other words, what you're going to do here is once you have all the heights, all you're going to do is add all of those function outputs together. That's this part right here in the square parentheses. You're adding all of the heights together, and then you simply multiply by delta x. So you can add together all the functions you determined, and then multiply by delta x, and that is your final answer. So let's do the problem, and I want to follow this strategy so you can see what I mean by all this. So let's start with the problem. Now the problem in your homework is most likely not going to give you a graph like this with these rectangles colored in. What you're going to see with the homework is going to be something more like just a statement. So here's a typical homework problem. Estimate the area under the curve and between the x-axis using 4 rectangles, so that's n, between x equals 1 and x equals 5, so that's b, and that's a, for this function 1 over x. So the strategy, the first thing, determine delta x. That's easy enough, because delta x is just b minus a over n. b is 5, a is 1, and n is 4. And so that tells us then that delta x must be 1. Now the second thing we should do here is determine if we're doing right, left, or midpoint. So I'm just going to say let's do right for now. So for this problem, let's just do right. So now we've made a determination. We now want to list all of the positions of where the rectangles are. And now to do that, for a right rectangle, we use our expression for right rectangles over here in the summary. Here's our right rectangle expression, which is what I have right here in the starting point. But I'm going to start filling in the information. So for instance, we know a is 1. So I just plugged in 1 for a. And we also know delta x is 1. So this expression simplifies down all the way to just I. So all the positions are simply given by I. And if I look at the strategy here, it's saying, well, let's list them out. Okay? So when I equals 1, we get 1. I equals 2, we get 2, 3, 3, 4, and 4. So that's what we figured out from this expression here. All of this simplifies down to just I. So there we go. I listed out all the positions of where the rectangles are. Now that we have where the rectangles are located, we can now figure out what their heights are. And we do that by plugging it into the function. And here's the function again, in case you forgot, 1 over x. So we're going to take all our x values, plug them into the function, and list it out. And so there we go. I listed them all out. We plug in 1, plug in 2, plug in 3, plug in 4. So that was this step right here. Determine all the function values and list them out. And so what do we got next? Plug all of this stuff into the area sum. So we're going to take this information here, and we're going to plug this all together. We're going to add all of these function heights together. So we had 1 plus a half plus a third plus a fourth. And we do have to get a common denominator of 12. Adding all of those together gets us our 25 over 12. So that's this part right here, summing all of these heights. Once we sum all the heights together, we just multiply by delta x. For this particular problem, delta x is 1. So we have 25 twelfths times 1, which is 25 twelfths. And that is our answer for the function 1 over x from 1 to 5 using 4 rectangles. Our estimate for the area under the curve is 25 twelfths, just a little bit greater than 2. So that's for right. Let's try left rectangles. I'm going to use the same strategy. I'm just going to remind you again, using our summary chart here, that left rectangles are given by this expression, a plus I delta x. And so notice I have that written again over here, but I'm plugging in now the information of the problem. We know a is 1, so I plug that in. We also know delta x is 1, and so I plugged that in. And so this expression then simplifies down to 1 plus I. So we want to list, we're on our step here, list out all the positions of the rectangles. So that means cycling through I from 1 to 4. So when I equals 1, we get 1 plus 1 is 2. When I equals 2, we get 2 plus 1 is 3. 3, we get 4, and 4 plus 1 is 5. So listing out all the positions of where the rectangles are at. Once we have all their positions, we can plug it into the function to get what those outputs are. Remember again, the function is 1 over x. So plugging in 2, 3, 4, and 5 gets the half, third, fourth, and a fifth. So that's this step right here. List out all the heights. Once you have all the heights of the rectangles, you're going to add all of these numbers together. So a half plus a third plus a fourth plus a fifth. So let's add those together, half, third, fourth, and a fifth, common denominator. That gets us a 77 over 60. So once we've added together all the heights, then we simply multiply this by delta x. And in this problem, delta x was 1. And so our final answer for left rectangles is 77 over 60. And the final example here then is the midpoint rectangles. So let me just remind you on our summary page here for midpoint rectangles, what our position formula is, our x sub I. So I have that written over here again, but now I'm plugging in the information of the problem. So a equals 1 and delta x equals 1. And so we have this slightly more complicated expression for midpoint. And now in our strategy, we're going to list out all the positions of the rectangles given by our position formula here. So the first position, when I equals 1. So just plug a 1 in here. 1 minus a half is a half. And then a half plus 1 gets us 3 halves. And you plug in 2, plug in 3, plug in 4. and you'll get these fractions. Once we have all the positions, remember the goal, the ultimate goal here is to get the heights of these rectangles. Now that we have the positions, we can finally get the heights. And so we do that by just plugging those numbers into the function. So our function here is 1 over x, so these all get reciprocals here. So the 3/2 goes to 2/3, 2/5, 2/7, 2/9. These are the heights of the function these are the heights of the rectangles. And recall back here that we can simply add all those heights together and then multiply by delta x. We're going to add all these numbers together. So 2/3, 2/5, 2/7, 2/9. Least common denominator is 315. So working all that out, and that all sums together, get 496 over 315. That's adding all the heights together, multiply by delta x, which is 1, and we get our final answer. That is our estimate for the area under the curve. So as a final tally, we had right rectangles, a little over 2 for our total estimated area. Our left rectangles was about 1.3. So notice which is higher, which is lower. So in this case, 2 is higher, so we would call this the upper sum. It's the highest estimate. And the left rectangles in this case is giving us the lower sum because it's the lower number. So again, I'm not a big fan of the upper-lower sum, but you'll probably see it here and there. And you simply don't know which is which until you crunch out all the numbers. You simply don't know. Only at this point can I finally tell you, oh, okay, 2 is the upper, 1.3 is the lower. And then finally for midpoint, which is more accurate than left and right, you can see it's actually 1.5, 1.6 about. So it's right between left and right in the middle there for the midpoint rule. So there we have it. I'm not quite sure how long this is going to turn out since I still have to do the editing on it. Hope this turned out to be much better than the written lectures. I still got a lot to polish up with this since this is my first experience with all this. But I really do hope this was a much better help for you and that we can get a strong showing on test 4, and integrals will be very important going into future calculus classes. So it is very important that I really try my best to get through to you this integration. So we will talk about everything we did today was actually algebra. Try to wrap your head around what we've been doing here, because our next lecture, we're going to take this then into calculus, and so we can start getting exact answers. So I will see you next time. Or I guess talk to you next time.